We have kind of an unusual probability question tonight that involves this notion of a repeated root. Now, let's just do a concrete example, make sure everybody remembers this. Let's say we have x minus 7 quantity squared. It's clear that this is quadratic, but that's just one root. That's just one root, namely 7. You know, 7's the only solution. You can call it a single solution or repeated root. There's some controversy on on that, but in any event, when you expand this out, you'll get x squared minus 14x plus 49. And this is just an example to understand what we mean by repeated root and how the discriminant is going to play a role here. Now, y'all recall the discriminant is the coefficient of x quantity squared minus 4 times the constant term. And it's actually 4 times 1, but there's none. This is a monic polynomial. So the discriminant here, and I'll just call it big D, is equal to minus 14 squared, which is 196, minus 4 times 49. But guess what? 4 times 49 is also 196. So we get 0 there. So that's the necessary and sufficient conditions for a repeated root to occur in a quadratic, is the discriminant has to be equal to 0. Okay, so now, so you guys are familiar with a dice. A dice, there's the faces are numbered 1, 2, 3, 4, 5, 6. So we're rolling a fair dice twice, and we're saying the first and second rolls, the dice show an A and B respectively. So it's real clear that A comma B all have to take on the values, and I'll just write like this, can be equal to 1, 2, 3, I'll just write them all the way out since it's such a small number, 4, 5, 6. Okay, so you can see that since they're being rolled twice, it's clear that there are 6 times 6 outcomes. 6 times 6 outcomes. All right, now the question is, how many of these outcomes involve a repeated root? Well, that's something you can almost do instantaneously if you just take a look. Well, no, I won't. It took me longer than that, but notice that the discriminant, you got to be a little careful here. B is normally what you see in the quadratic, right? A B right here and a C right here. Instead, they have A and B. But your discriminant is A squared minus 4B equals 0. Well, under what circumstances, with A and B just taking on these 6 values, can this be equal to 0? Now, a lot of you may have spotted it by inspection already, but it's very much related to just y squared minus 4y. Let's say, equals to 0. Okay, so you see you can factor a y out of this, and you get y times y minus 4. And of course, 0 is not relevant according to this probability problem. You know, this is a dice problem where you don't have a 0 for a face value. So you get y equals 4 here. So it's the very same thing right here. You would have to have A equals B equals 4, okay? Which is just one outcome. Okay, that is just one outcome in our outcome space. Remember, the outcome space is A comma, it's a set of this form A comma B, right? And there's 36 of the possibilities here. Let me put that in set just for, okay. And that's where this 36 comes from. A can take on any one of 6 values. B can also take on any one of 6 values. But A equals B is just one of those events, right? And that would be A equals B equals 4. Okay, 4 squared minus 4 times 4 is 0. And so that's just one event in this space. In other words, let me write it like this. 4 is the only member of this set that meets the conditions of the problem. So just one element in our 36 element sample space, and so we get 1 over 36 is the answer, folks. Kind of a fun problem. Wei Tan showed this problem where it was just if you had distinct positive or distinct real roots. Okay, so I just twisted that a little bit. It's one of the SMO. I don't know. I think it's SMO Junior problem type. It's a rework. Not a rework, but it's the same kind of problem worded slightly differently with a slightly different goal. But anyway, the answer to the question is 1 over 36. Okay. Thank you all for viewing.